Well, good afternoon, everybody. I'm here to tell you an amazing story. It's the story of how a small team of AFRL researchers solved a problem for the military and in the process ignited a revolution in ground-based astronomy. The technology is called laser guide star adaptive optics. It was developed to get high-resolution pictures, images, of Earth-orbiting satellites. But when we started that project in 1982, we had no idea that in 20 years, astronomers would be using that technology to do this. This is a highly magnified view of the center of our galaxy. It's 25,000 light years away. The bright flash that you see in the center of the picture is interstellar matter being compressed by the strong gravitational forces of that black hole. I forgot to mention there's a supermassive black hole there. And that material is superheated to a plasma and releases enough energy that we can see it this far away. These images were made by the 10-meter Keck telescope in the Hawaiian Islands using laser guide star adaptive optics. And they would not have been possible without that technology. We're going to talk a little bit more about what the astronomers are doing in a few minutes. But first, I want to go back to the original problem that started all this and get a little technical to describe what the solution is. So it's 1980, the Cold War is raging on. The United States is desperate to find out what the Soviets are doing in space. In order to do that, we need high-resolution pictures of their satellites. But our ground-based telescopes, when they take a picture of a satellite, they get this. And the problem is the following. If I had a large telescope, and we figured we needed about a 140-inch telescope to see the details that we were looking for, this is the kind of image I would get if I had a perfect telescope. But what I have to do is put that telescope on the ground, and I have to look through the atmosphere, Earth's atmosphere, which is a turbid medium. It's composed of regions of different temperature, which cause the speed of light to change as it propagates through it. And so when we try to focus light that's been distorted like this, we get a blurry image. And our 140-inch telescope gives us no more resolution, no more clarity than a 4-inch telescope. Because it's bigger, it collects more light, and it gets that blurry image, only it gets it quicker. That's the only advantage. Not a very good result. Well, this is a problem that astronomers had been faced with for 400 years. And a problem, worth working on, actually. And at about this time, a new technology called adaptive optics was emerging. And here's an animation that shows how it works. It basically involves, here comes light from our telescope, bounces off of a mirror, and then a beam splitter which samples the light. And the idea is to analyze the light with that beam splitter and sensor to find out what those distortions are, and send a command with a computer to a mirror whose surface you can change. It's a flexible mirror. We call it a deformable mirror. And when we do that, we can so adjust the mirror to exactly remove those distortions. And we get back to essentially a perfect image. One of the rubs is you need to do this very fast because these distortions are changing hundreds of times per second. So you need a fast computer and you need a fast mirror. So here's what it looks like in real life. This is an image of a star on turbulence, and here it is with adaptive optics running. And we actually see in this image that there's two stars there, which is difficult to see in this image. And that gives you some idea of why this is so important for astronomy, as well as for space situational awareness. That's the kind of resolution that we need in order to look at fine details on a satellite. In this particular case, these two stars are equivalent to the headlights of a car at about 1,200 miles. So in 1981, the Defense Advanced Research Projects Agency built the first adaptive optics system for real, because we at that time had the technology. We thought we could actually make it work, put it on a 60-inch telescope on the island of Maui that was especially designed to track low Earth orbit satellites. And it worked for bright objects, but it did not work for faint, small satellites. The problem was we needed an independent source of light. There just wasn't enough light, so we needed a brighter source of light that could be used to just measure the atmospheric distortion and run the deformable mirror or run the adaptive optics. Astronomers sometimes use, when they're making images of faint objects, they use an additional star, a star that happens to be in the field where they're making the measurement, to guide their telescope. And they call those guide stars. What we needed was a guide star that served a slightly different purpose, something bright enough to give us enough light to make a wavefront distortion measurement in a small enough time that we can make the correction before the atmosphere changed again. So one of the researchers that was involved in that first adaptive optics system, Julius Feinlieb, was out on the ground one night at Maui and watching the laser that was used to measure atmospheric transmission. It pulsed at about 1 pulse per second. And as the beam goes up through the sky, you can see it. I mean, most of you have seen a laser light show, or if you're old enough, a searchlight. And so he got the idea. Could we use that light that's being reflected back off of the molecules in the air to make a wave, to be our independent bright source to make that wavefront measurement, independent of the target? And so the idea would be focus the laser in the sky above the telescope in the general direction of the thing we're looking at, and then pick that light off of that color from the laser only and send it to our sensor and back to our deformable mirror. And then, even if the target is faint, we can make a longer exposure with our camera, all the time correcting for the atmospheric distortion. So he proposed this idea to the government in the fall of 1981. I was lucky to be at the meeting. We took the information, we analyzed it, and we determined that because the laser guide star in this case, caused by this scattering off of air that we call Rayleigh scattering, first described by Lord Rayleigh in the 1800s, absolutely amazing, and it's what makes the sky blue, that was not going to work for a big telescope. It was only going to work for a 40 to 60-inch telescope because the laser was at a different range than the target. What we needed was a higher altitude guide star. Well, in the summer of 1982, we were summoned by the Jasons. This is a high-powered academic group hired by the Department of Defense to review new projects. When we described our theory of the Rayleigh guide star, the chairman of the committee, Will Happer from Princeton, suggested a different approach, one that we hadn't heard about. It turns out there's a thin layer of sodium atoms 60 miles above the Earth that's replenished by grain-sized meteors, basically remnants of the solar system. As they burn up, they leave small amounts of sodium atoms behind, and because sodium is light and there's nothing else up there for it to react with, it just hangs out. So if we could shine a laser up there and cause those sodium atoms to glow, just like the sodium street lights you see, we could use the light coming back down through the atmosphere from those sodium atoms to make our wavefront measurement. and we would have a higher altitude laser guide star, one that was high enough that we could correct our 140-inch telescope. And as it's turned out, it's now being used to correct 10-meter telescopes. And so here's a picture on the inset of what that looks like from the telescope. The brown dot at the top is the guide star caused by the sodium glowing at 60 miles high. The streams of light that you see below it is Rayleigh scattering, just like, we could use for a Rayleigh guide star. So we're not interested in that light in this case. We're only interested in the light coming back from the sodium layer. And so in our sensor, we just block out the other light. So we had two approaches. But we didn't even know, could you make a wavefront measurement from a laser? We knew you could make a wavefront measurement, the distortion in the atmosphere from things like stars, but could you do it with a laser? And things like satellites, because we had already built a system that did that. So DARPA proposed two experiments, one to test the Rayleigh concept and one to test the sodium concept. I immediately raised my hand and volunteered to do the Rayleigh experiment because that would work with any laser wavelength, whereas the sodium experiment required a very sophisticated laser. So in the fall of 1982, we got $100,000 to do this experiment. That was a lot of money then. At least it was a lot of money to me. So I found at Kirtland Air Force Base, in a very remote part of the base, an abandoned building that had been used previously in a project called Project Delta, where they shot down a drone with a high-powered CO2 laser. And we set the experiment up there. And the part I left out was DARPA decided to classify all this very highly, very limited access. There were fewer than 100 people in the country that knew these two experiments were going on. So we had to do it in secret and as quickly as we could. So we had two objectives. One was, could we make a wavefront measurement from a laser? And number two was the theory about the fact that we would make an error using the laser compared to like a star or a satellite correct. In a year's time, we were able to accomplish both of those goals. And that paved the way for a system, an adaptive optics system using a laser guide star. We were only making a measurement here. We were not making any corrections. So we were, as we say, making the measurement open loop. So we got busy. We modified the facility to accommodate a telescope. The only laser that would work was a high-powered copper vapor laser built in England. I took a trip to England to look at the laser. They were extremely curious about why a person from the Department of Defense wanted to buy their laser, couldn't tell them anything. We designed and built the optics and the sensors and the high-speed electronics that would be needed to close that loop and control the deformable mirror. And in May of 1987, we took delivery of a 60-inch telescope. And by February of 1989, we had integrated all that stuff into the first working laser guide star adaptive optics system. And it worked. And it was still classified until May of 1991, in which time it was first publicly released at an American Astronomical Society meeting in Seattle, Washington. This photograph was actually made the day after I gave the talk and at a press conference. And seated at the table is Dr. Charles Townes, the Nobel laureate for inventing the laser. And he had been involved in the project for some time, was a strong advocate of this technology for astronomy. And of course, actually, those of us working on the project were as well, because we knew this was going to be a big boost for astronomy. So in March of 1992, we had a 3-day workshop at Kirtland Air Force Base in Albuquerque. And we invited astronomers. Well, we didn't know if they were going to show up or not. 250 showed up. And we had to move the meeting location 3 times because it kept getting larger. So we were overwhelmed. And I was able to get the fellow that wrote the first paper that suggested adaptive optics, a fellow, an astronomer from Palomar Observatory named Horace Babcock. I got him to come and give sort of a keynote address at the meeting. And he stood up in front of us and he asked us a question. What took you so long? Because he wrote the paper in 1953, it's now 1992, almost 40 years later. But this was the beginning of a great relationship between the Air Force and the astronomy community. And by this time, that facility that we had grown with the addition of the 1.5 meter telescope, the 60-inch telescope, and it became known as the Starfire Optical Range, or the SOR. And so for about 10 years, we operated that system, and we shared it with astronomers through a program at the National Science Foundation in which they could come and use the telescope and adaptive optics and learn what it could do and what it couldn't do. And so some really interesting research came out of the effort. And for a long time, we had more refereed papers in the astronomy community using this technology than any of the real observatories. So we did some science. Here is one of the earliest things we did. At the center of the Great Orion Nebula, there are 4 stars called the trapezium. And so this is a really crummy image made with our 60-inch telescope through really bad seeing. I just want to strike a contrast. So at the same time we took this image, we turned on the laser guide star adaptive optics, and we got this picture. And this happens to be through a special filter that allows us to see ionized hydrogen. Some of you have heard it called hydrogen alpha filter. And when we use a filter that blocks that or does not allow any atomic transition, we get a picture like this. And this filter is called a continuum filter because it only shows us black bodies like stars that are emitting at all wavelengths. So everything you see in the picture on the left that you don't see in the picture on the right is ionized hydrogen. And so all of those little objects that look like stars are not yet stars. They're clouds of hydrogen collapsing under gravitational forces trying to form a star. And so this is a stellar nursery. And there's another thing going on in this picture, and that is some of these objects have little tails after them that point away from that central star. And so the solar wind created by that central star is trying to rip those objects apart. And so there's 2 competing forces here. So just one picture, a lot of interesting science. After we did this work and published it, the Hubble Space Telescope was repaired. As you remember, it had an optical problem. They made the primary. It was a perfect primary mirror. It was just the wrong one. And so they had to put an optical corrector in order to fix that problem. But once they had that fixed, the very first set of objects, among those objects that they looked at, this was a region they looked as well. And so they saw the same thing we saw with higher precision, higher resolution. We also were looking at satellites during this time with the telescope, and which was, after all, our primary job. And one afternoon, I got a call from Jim Breckenridge at the Jet Propulsion Lab in a major panic. And they had been involved at JPL in building the payload for a Japanese Earth resources satellite called ADIOS. And it had gone silent the day before. There had been reports of a collision in space, more space debris. And could we take a look at it with our adaptive optics system? Well, that very night, it passed over the SOR, and we took video images with our acquisition camera. I wanted to use the science camera for higher resolution, but Jim wanted a video. And I called him up after the pass, and we were talking about what I was seeing. But don't you see the solar panel deployed along the boom? No, I just see two cylindrical-looking objects at the far end of the boom. Oh my God, the solar panel has become disconnected and rolled up like a party favor. And so we had $2 billion worth of space junk. Well, they did redesign the latches on the next mission. So that was one of the things we learned. So while we were doing that, my vision was still a 4-meter class telescope with sodium laser guide star adaptive optics. And one of the issues was, how do you make a 3.5 meter or a 140-inch diameter mirror quickly? A fellow at the University of Arizona, Roger Angel, had invented a new way to do that. You basically take chunks of glass, put them in a furnace, heat the furnace up, melt the glass, spin the furnace so that you now generate a parabolic shape on the surface, and that greatly reduces the time required for grinding and polishing. So when I started this collaboration at the University of Arizona, this project was still classified. By 1994, we had the world's largest telescope that could track low Earth orbit satellites. And by 1998, we had put together the adaptive optics needed to run on that telescope. 1,000 class actuator adaptive optics system. And by 2004, you'll notice it's taking longer, we had a sodium guide star laser. So today, every large ground-based telescope, astronomical telescope, is using this technology. It has been incredibly embraced by the astronomical community, and it is literally creating a revolution in the science of astronomy done from the ground. And the astronomers are developing new techniques, more advanced. They're even using robotic telescopes that use ultraviolet lasers using Rayleigh scattering that have no operators. And they're making incredible discoveries. These are amazing discovery machines. One of the things we learned was about everywhere you point the laser and the telescope, you discover something new. So here's an example, the galactic center again. And a group at UCLA is mapping the orbits of stars around the black hole to determine its mass. 4 million of our suns. So don't get too close. We're discovering new planets and able to image those planets and put spectrometers on them in order to characterize their atmospheres. And of course, one of the holy grails of astronomy is discovering life on another planet. We're also being able to study the structure and evolution of structures in the universe. In fact, today astronomers want to discover this, or to study this entire cosmic timeline of nearly 14 billion years. And in order to do that, we need bigger telescopes that are corrected with adaptive optics so that we get the advantage, the sensitivity advantage of those large telescopes. And today, the two largest ones being built because of this technology are a 39-meter telescope in Chile and the 30-meter telescope on the Big Island of Hawaii. So I'd like to finish with some philosophy and tell you a few things I've learned in my career at AFRL. I used to have a chart that was titled something like, "Everything I need to know about doing research at AFRL, I learned at the SOR." It was the kind of analogy or parody of the book that was popular at the time, "Everything I Need to Know About Life, I Learned in Kindergarten." So one of the top items on that chart was work on problems that matter, that are important. In our case, it was developing a new capability for space situational awareness. In the case of astronomy, it's solving a 400-year-old problem and now being able to build new telescopes and new instruments that will allow them to unravel the secrets of the universe. The other thing is to build a vision and a goal, and then believe in it. You know, when I started this in 1982, my vision was a 4-meter class telescope with laser guide star adaptive optics using sodium lasers. And it took 20-some years, but I never, ever lost sight of that vision. And I never once believed that it could not be done. There were people that told me it couldn't be done, but I just solved every problem that came up in turn and believed that it could be done. And we finally realized that vision. So it requires working hard. In my case, that makes up for not being so brilliant. My daughter used to tell me when she was young, "Dad, you're working so hard, you need to get in a slower group." So maybe that's right. Maybe somebody else could have done this more quickly. But there are opportunities that come along, seize those opportunities, and take risks. This chart is full of pictures that represent that mantra. Every one of these pictures represents something that was either never built before, or was built at high risk, or expanded the scope of the technology. So we were always pushing the boundaries. Well, you can't do that. Well, let's figure out maybe we can do that. So one of the most important aspects of a great leader is the ability to, especially in the research and development business, is to understand the engineering problems at hand. And you know, what are the key things? What are the long poles in the tent? And it's really kind of sorting out the real problems and not worrying so much about the ones that aren't perfect. And then what goes with that is finding people that have the right skills that can be placed against those problems to solve them. And when you find the match between the people and the problem, amazing things happen. Here's a picture of one of those people that I actively recruited. His name is Ray Ruane. He started out as a sergeant in the Air Force. He's been at the SOR 45 years. And when he retired from the Air Force, he became a civilian. He's still there. He's the kind of guy that puts the mission first, has an incredible amount of skill and wisdom about working on telescopes. You can't do without him. The other thing that I've found very powerful in terms of a management approach is to allow people to own their work. People involved in R&D, the most important fact or the most important thing to them is intellectual property. It's being associated with something they designed or built or worked on. They really want to be part of the solution to a problem that matters. They want to be stakeholders in that. They don't really care what kind of office they have. They don't care how far they have to drive to work. They don't even really care much about how much money they make. They're passionate and dedicated about the solution to the problem. So at the SOR, we talk about Ray's telescope, Jim's optics, Carl's alignment, Ann's seeing instrument, Naomi's network. So you get the idea. And when you have people like that, it's pretty easy to build really effective teams. And at AFRL, we have a unique opportunity of getting the best of the best, because we can build teams out of military, civilian, and contractor personnel, and make them work like a well-oiled machine. You know, when you have this kind of a group, they have a lot of self-confidence, and there's little or no competition amongst them. And they respect and use the work of others and each other. So in this picture, we have the optics group, the analysts and software group, the team that built the sodium guide star laser, and the telescope group, just as an example. So how well does this philosophy work? This is what the SOR looked like when I arrived in the late 1970s. That building halfway up the hill on the right is where we did that very first experiment. And when I left, or actually 1 year before I retired, in 2005, the facility looked like this. So we took a bump of granite in the desert and in 2 decades turned it into a world-class optical research facility. It's been said that ideas are what changed the world. I'm beginning to believe laser guide star adaptive optics is one of those ideas. It has given a great capability to the Air Force for space situational awareness, and it has provided a new tool for astronomy that's the most important advancement since the invention of the telescope. And this was all because of a single idea. And it was because a dedicated team of researchers were passionate about what they were doing, had a vision that they believed in. And it's because AFRL is a place where opportunities exist that don't exist elsewhere. I firmly believe that this work could not have been done as quickly as it was anywhere else other than AFRL. It's been a really rewarding experience to be a part of it. And so I charge all of you, go out, find that problem that matters, build your vision, and believe in it. Work hard, don't be afraid to take some risks, and seize those opportunities when they come along. Thank you.